ready.
Photography
നമുക്ക് അറിഞ്ഞൂടാ കേട്ടാ. ഇല്ല, കണ്ടില്ല. നമ്മളവരായിട്ട് ബന്ധമില്ല, അതാണ് വേറെ ഡിപ്പാർട്ട്മെന്റ്.
ഫോട്ടോ എടുക്കുന്നുണ്ടോ?
വീഡിയോ വൈഡും ബാക്ക്ഗ്രൗണ്ട്. Yes, of you. Yes.
Professor Chandrabhas Narayana, Professor Trivandrum, VC IIST, and Professor Kurivula Joseph, Pro VC IIST, all faculty members and dear students. Good afternoon. So, as we know, in IIST, we instituted this colloquium series for encouraging interdisciplinary dialogue among faculty members and students from different backgrounds, ranging from sciences to engineering to humanities. So in the past, we had very eminent personalities coming from India and abroad from premier institutes for delivering this colloquium lecture. So today, we have an eminent, very eminent guest, Professor Chandrabhas Narayana with us for delivering the 5th colloquium lecture. Actually, he's not a stranger to IIST. He has visited IIST many times, mainly in connection with conferences organized by Department of Chemistry. And today he is giving colloquium lecture in IIST. So I'm very privileged to introduce Chandrabhas Narayana to this audience in a formal way. So Professor Chandrabhas Narayana is currently Director of Rajiv Center for Biotechnology, Trivandrum. He is actually his work is internationally recognized for the work in Raman Spectroscopy and its applications in understanding protein structure, drug-protein interactions, and diagnostics technologies. His group has significantly contributed towards tailoring the surface plasmon reference property of silver and gold nanoparticles for application in the area of surface enhanced Raman spectroscopy. His group is also working in MOS, metalorganic frameworks, and finding microscopic origins of observed properties using Raman spectroscopy, which has led to a better understanding of the synthesis and structure and properties of metalorganic frameworks. And Chandrabhas Narayana earned his PhD in physics from IIST Bangalore and pursued his postdoctoral research at Cornell University. And before joining RDCB as director in 2020, he served in Jawaharlal Center for Advanced Scientific Research, Bangalore, where he held several leadership roles, including dean and chairman of the Chemistry and Physics Research Unit. And Professor Narayana is a fellow of the Indian Academy of Sciences, the Royal Society of Chemistry, and the National Academy of Sciences India. His contributions have been recognized with many prestigious honors, including ISAS Raman Award and Mr. Raman Spectroscopy Award and the MRSI Senior Award for Superconductivity and Material Science. And Professor Narayana is editorial board member of reputed journals, the Journal of High Physics, High Pressure Research, Journal of Biomaterials, and Nanobiotechnology. And he has nearly 200 research publications and several international papers distributed. And his work is always known to do the bridge the gap between physics, chemistry, biology, and healthcare. With this very introduction, I extend a very warm welcome to Chandrabhas Narayana. I also welcome Professor Panda Banerjee, BCIST, who is giving all sort of support for this program, and faculty members and dear students of this program. Thank you. And I request Professor Chandrabhas Narayana to deliver this.
So first of all, Dipank and Sundari, for organizing this. It is indeed a pleasure to come back to IIST. Multiple times I have actually been here and delivered lecture. And this lecture again, because it's a very diverse audience, I will actually try to make it as simple as possible, because I want people to take it back that this is a technique which can be used not only in physics, chemistry, and biology, but also in the space missions. Okay. So I was actually involved, I should tell you that with LEOs, I was actually working on trying to find out if I can actually have on the Mars mission, if the Raman probe could be there in the landing. In the probe which lands on the Mars, because ice is one of the very important things which people are actually looking at, and the various phase diagrams of ice, if you look at it, it can be detected by Raman. And so you can actually be very sure about what kind of water is there in this environment, because the pressure, temperature, and also the kind of environment it is there, you can actually find out. And that was the proposal I actually went to in front of the ISRO people, and then I realized it's tough to get them convinced for doing anything. But I really like the professionalism of ISRO and space science, because that's how they have actually been able to do this. But I am sure that at some point of time, I will be allowed. Another reason why I was working with LEOs was that you are actually putting up telescopes in the sky, in the sky, and telescopes generally now you want to replace the glass with silicon carbide. And one of the major issues in silicon carbide is that polishing the silicon carbide is a very difficult process, because you can actually have fractures. The binding doesn't happen. And Raman is one of the best ways to actually find out whether the binding is good, so that you can start the whole process. Otherwise, the process will be wasted halfway. And I actually designed a robotic arm-based Raman for LEOs. And unfortunately, the person who was actually involved with me passed away very early at the age of 50. And that project didn't go further up. But the whole idea was that you can actually do these kinds of things. So I just wanted to motivate you that this is not just for some research. There is a lot of things you can do with this tool. And another reason why I'm always excited is because this is the only discovery which got the Nobel Prize, and it is actually of India. And all of us should know what this is. So with that in mind, I'm going to actually start. How did actually Raman come to this kind of a idea about Raman scattering, and how did it actually become a very powerful tool? So the very important thing which Raman actually was very fascinated, and all of you should be, observations. If you are a good researcher, you should have a very good observation. So he started observing while he was traveling in his ship that the sea is blue, but sky is also blue. Is the same phenomena which is there for the sky that leads to the sea as and all of us know sky is blue because of scattering. And so the question was whether water is also blue because of the scattering of light. But that was something which Raman didn't agree. But I also actually tried to prove that point, that why Raman was not convinced. So I take actually, if you have looked at the blueness of your water, if you look at it in the sea, it it is not, it is much darker than the sky. Now, why is that it's darker? But in certain cases, the water doesn't look blue, but it looks greenish. And especially if you have taken photographs and seen, you would realize that swimming pool is always blue, and sometimes shallower end of the swimming pool looks greenish. So these are things which are very interesting. If it was actually scattering and giving you the blue color, then it should have been the case. But then Raman, being Raman, actually wrote a paper on the color of sea. He published it in Nature, which is very difficult journal to publish. And I want you to realize that he published this from where? Harbor. So he didn't even go to this lab. He wrote the paper in the duration of the 2 months. He went from India to UK and come back. He has actually written a paper. The whole observation is very simple because his language is also very simple. You can see, I'll highlight this, is that he knew that if water was actually scattering, there should be some amount of idea about how the scattering is happening. Now, at the time when Raman was actually talking about this, Lord Rayleigh, who is actually a famous guy, who he said that it was a reflection of the sky. He said the blue is the reflection of the sky. And if you know your 12th standard textbook, I'm not taking anywhere else, the 12th standard, you would have seen this picture. Any unpolarized light gets partially polarized when it is reflected. So what he did is that he actually took a Nicol prism. He used to always carry gadgets around him. He took the Nicol prism because it is a polarizer. So he started looking at it through the polarizer. And if it was a reflection, then I would actually, at particular angle of the reflection, I should get no light or very dimness of the light. So he was doing this whole experiment throughout the journey which he was doing. And you see that this is what happens. Most of the times, very bright sunlight, when you take a photograph, you don't get features because of the reflection. If you put a polarizer, then immediately you start seeing features which were not visible. So this is what he used, the idea that time. Okay. Now we have cameras with polarizers and all. So this is the prism he was actually using. So he wrote this very nicely, that he kept the water in such an angle that the sun is behind him, so the reflection will come into his eye. So he is using this thing. So he says, very smooth patch of water, he's looking on the river, I mean on this thing, and then trying to do this whole experiment. And what he finds is that it is in the Mediterranean Red Sea, he finds that instead of becoming dim, the light, it becomes much more brighter. That means it has to be not the reflection. And he disproved what was said by Lord Rayleigh. And then later on, you can actually understand, now we can understand that the color of the water is not because of anything else. It is basically the absorption of light. So a water body actually absorbs first the red light, then the orange light, yellow light, then the green light, then the blue light, and then all the light. Because you know that in deep sea missions, you need a torch light. If this light was not getting absorbed, you don't need you no need light to take a photograph. So absorption of light was there. Now, why does the light come back if it is getting absorbed? Because you have refractive index changing. On the top, the surface, the light is actually, density of water is higher because of the salt content. And as you go down, so it is denser to rarer, it will reflect back. So it is basically the light, blue light, which is coming back to your eyes. And that's what is giving you the blue light. If the depth of the thing is less than 1.2, 1.3 meters, then you start seeing green light. And the green light is because green is more sensitive to our eyes compared to the blue. So that's why you will see in the swimming pool, if you take a photograph, at the 4 feet level, it will be greenish. And if you go to 9 feet, it will be bluish. Tiles are not the reason. Tiles are actually supposed to be white. Okay, if you want to have a good swimming pool. So this is what is the thing which motivated him. But later on, he started thinking, why is it more darker blue? It is not just blue, it is darker blue. The reason is there is a lot of scattering which is also happening with the molecules of water. So when a light falls on any material, you will see that the light gets transmitted. This has been told to you. It gets reflected. This is the major things which would happen. Alongside with this, there is some amount of absorption which happens. Also, you have sometimes luminescence. That means fluorescence, phosphorescence, or luminescence, which happens. This is the major things which happen. But alongside with this, you also realize that there is scattering. And I have written a word called elastic scattering. The elastic scattering is like elastic collision. Now, when you talk about elastic collision, it means that the momentum is changed when you actually have a collision, but energy doesn't change. Elastic collision, the energy remains the same. So whatever was the kinetic energy with which the ball went and hit the wall, the same kinetic energy it comes, then it is elastic, right? The wall doesn't have any movement, so it is actually zero kinetic energy before end of the same kinetic energy. So similarly, if we are talking about elastic scattering, that means energy of the light doesn't change. And energy of the light is related to h nu, the frequency, and frequency is related to the color of the light. So if there is no change in energy, that means no change in color. So the same color comes out in all directions. So it is different from reflection. It is actually in all directions. Reflection has to follow the rule of Snell's law. That is, angle of incidence is equal to angle of reflection, right? So now I actually leave the students with a question. How do I see you? Which of these phenomena are the reason for I see you? I leave this to you. Try to answer this. And there are reasons why you will realize that there is an answer which day-to-day life you are doing things which will tell you how do I see it. Is it reflection? Is it scattering? Is it any other phenomena? Please think about it. But alongside with this, Raman actually said that there is also red shifted and blue shifted light. That means inelastic scattering of light. That means the light color changes. And this light color doesn't mean that green becomes red or green becomes blue. It is red direction. So the little more frequency decrease or frequency increase, which we are talking about. So when we are talking about that, so this is what Raman actually discovered, and this is why this technique is called inelastic scattering of light. Okay. And now how do I prove that inelastic light scattering happens? I can do this experiment very easily right here. So for that, I need a laser. All of us know that monochromatic light it is. You can see the dust particle in the room, in a dark room, you can see the scattering from the dust particle. That's the blue color. And I have taken a transparent liquid, and this is nothing but cyclohexane, which is a transparent liquid. And you can realize that this scattering happens from the liquid at this point. You know that laser light is going in this direction. For me to see the light, I need the light to fall into my eyes. So naturally, this light which is coming out is 90 degrees to it, and that has to be the elastic scattering. Now, don't get confused with the color. Color is white in color it's seen. It is not white. It is actually saturation of your detector, and the detector gets saturated, and that's why it looks like whitish. But if you are looking with your naked eye, it will look blue in color. So this is the elastic scattering of light coming from the liquid, and you see how intense it is. And that gives you a hint why I can see you. Now I put a filter which filters out the blue light, and you can see that the elastic scattering of light from the dust particle has got completely disappeared. Now I see different colors. This is Raman scattering, and this is the Raman scattering which is coming out of cyclohexane. Now this is very important, that when you are actually having inelastic scattered light, I want to see the inelastic lattice, to see the components what are coming out. I just need to disperse this light. I collect the light, put it in a dispersion agent, and disperse it. So that's what Raman actually did. He actually took the sample, passed the sample, filtered the light. He passed it through a prism. And this is a prism which actually has a photograph attached to it. He takes the photograph, and this is the one in IIST where he got the Nobel Prize for. And this is costing less than, at that time, 10 rupees. Now it is about, you can make this whole thing for 250 rupees. And that's all got a Nobel Prize. So one of the learning for you is that very big instruments are not needed for getting Nobel Prize. Good ideas are necessary. And what did he get? He got this shifted light. you see the elastic scattered light, then this is actually the blue shifted light, and this is the red shifted light. And that's what he actually photographed and said, new origin of new light, and he published that in a Nature paper in 1928. And that is what got the Nobel Prize in 2 years. For a very interestingly, this didn't even actually know what was the use of it. But today, when I am actually going to talk to you, it has multiple uses of Raman, and that's why that was actually. Now, if you really want to do a simple system of Raman, you can actually do it very easily. You take a laser. This is a 1,000 rupees laser which is available in Amazon, and you put a filter which makes it monochromatic, and then you pass it through a sample, and then you have a filter which actually filters out the green light. And now, because you know that collecting all the light, best way is fiber. So I use a fiber to collect it. So there is a collection optics which connects it to fiber. Now this fiber actually is going to put it onto a mirror, and I use, instead of a prism, I use a grating, and I can actually get the dispersion of the light. If I disperse this light and take an SLR camera and take a photograph, what do I get? I actually get this elastic scattered light. So I told you, if my detector is saturated, it's going to look like it's actually the green color. And now you can see slightly different green, red, orange, and all of those colors are coming. Now, what you can do is you can digitize this. And if I digitize it, I actually get this. This is the elastic scattered light, and then I start getting inelastic scattered light. Now, this is what Raman spectra looks like. Now, why do you get such a spectra? Because there are certain things which are actually making this light to shift. Naturally, some energy is lost from the light. In this is red shifted light. So energy is lost. If it is blue shifted, energy is gained. So something is giving energy to the light, or something is taking energy to them. And that is because of the vibrations of the molecule. And now vibrations of the molecules are very unique. Actually, you have two atoms connected to each other. This is exactly what you have been taught in 12th standard, two balls connected with a spring. So any bond is considered as a spring, and any atom is considered as two balls. So these two balls have only one frequency. You know that degrees of freedom, it will tell you only one vibration is possible. And this vibration is stretching. So irrespective of whatever your diatomic molecule is, hydrogen, nitrogen, oxygen, you have HF, HCl, any of these things, all of them are diatomic molecules. They will have only one frequency, and that is stretching. But that stretching frequency has an energy, or the frequency associated with it is unique. And that is what makes it unique, because you see, I have taken HF and I have taken HCl. The only difference between HF and HCl is that Cl is heavier than fluorine. And the moment it is heavier, you see that the energy, of course, I have written in another unit, which is called centimeter inverse. And I know that you will be able to guess 1 by lambda is frequency. In some approximate terms, you have to multiply with a constant, and you will realize Hc is the constant, Planck's constant into velocity of sound. And then you will get a frequency, right? So that is what is there. So this is something like 500 milli electron volts. So this is 500 milli electron volts, and this is actually, you can see that this is about 300 milli electron volts. So the frequency instant. A simple way to understand is, heavier things are sluggish and lighter things are faster. So you will see that lighter the atoms, the energy required for them to vibrate is higher, or they are more energetic, and lesser it is. So now you can see nitrogen, if I have N2 and if I have oxygen, you can immediately know where the frequencies would lie. It's very easy to calculate. So this becomes like a fingerprint of the molecule. I add one more atom, and specifically I've added it non-linearly, means it's not linear. And water molecule actually has a vibration which is symmetric stretching. All the atoms are moving out and in, and the asymmetric stretching, and then bending, symmetric bending. Any molecule of this shape will have only these three vibrations. It cannot be different. And the frequency depends on the mass of the atoms and the connection between them, the spring constant. Okay, so basically that is what is the reason why we are having this vibrations. Now, very importantly, you realize that bending a bond is easier compared to stretching a bond. So naturally, the energy required for the stretching is much more than the bending. So this is very easy to understand. I said that any molecule of this shape will give me the same vibrations. So if I take CH2, CH2 looks the same, right? So its vibration should be the same. Of course, it is same. You can see symmetric stretching, asymmetric stretching, symmetric bending. But CH2 is different from water molecule. Because CH2, you have forgotten there is two tails behind that. There is an R group which is there. It's a heavy R group. So naturally, it doesn't involve itself in vibrations. So naturally, you will also have this happening. Because it's anchored, so it can do this, right? It can do this, and it can do wagging. So all of those vibrate. So naturally, the atoms, way it is connected, it gives you, even though the shape looks the same, it gives you a different kind of environment. So this is why it's a fingerprint of the molecule. And it actually, I can tell the structure of a molecule by just doing the Raman of this thing. Now, I told you, like this R group is there, right? Now, instead of that, if I actually have CCl4, now that's a tetrahedral molecule. Now, the moment I have a CCl4, because that is not a heavy atom, all are chlorines, this actually is the symmetry. You can see there are, any tetrahedral molecule will have this spectra. So CH4. So now you know that CH4 is found in extraterrestrial thing, methane, clathrates, various other things. All of these things can be actually identified. So that is why these kinds of experiments are very important. And they're unique. Now you see that you have chlorine symmetric stretching, asymmetric stretching, symmetric bending, and asymmetric bending. So this is the only vibrations which will be there for any tetrahedral molecule. It doesn't matter. But the energy associated with this will be dependent on what is the atoms connected to it and what is the way it is connected. So if I have an SO4, I will have the same spectra. If I have a CH4, I will have a similar spectra. But the energies will be different, so I can actually identify what is the molecule. And what environment it is there, it will tell me what is happening. Now, very importantly, if you really look at very carefully this symmetric stretching, if I see it was not actually looking like a single peak. Now, what is happening is that there is some other interferences happening. Whenever you are doing any spectroscopy, whether it is IR, NMR, you are doing mass spec, any of these things, if you are thinking that there are multiple peaks, one of the best ways to actually resolve it is just lower the temperature. So when you lower the temperature, the width of the peak actually changes. You can actually see this. Now you realize that this is not one peak, but it is actually having 5 peaks, and 1, 2, 3, 4, 5. Now the reason for this is very simple, because chlorine actually has relative abundance of 3:1 in 35 and 37, and the mass is different. I told you mass actually is different. The frequency of vibrations will be different. Now you realize that actually I have just inverted it, and you can see the highest energy, that means highest frequency, is actually related to all lighter atoms. That means CCl4 with all 35s. Now you can see next one is CCl4, 3 35s and 137, and relative abundance is highest. So you see the peak of that is the highest. Now you can actually guess the next one is 2 CCl35s and Cl37s too. Next two you can easily see is because of 3 CC37 and 1 Cl35, and this is 4 of them 37. That means isotope effect. So you can actually see isotope effects actually also there. And now you realize the importance of it. Now, why didn't I talk about carbon 13, carbon 14? Because the relative abundance is too less for C13 and C14, right? So that will not be shown up so easily. Now you can realize how important the mass is. So this actually tells you a lot of important things to come out. Now, finally, I'm saying that I proved the point that it is a fingerprint of the molecule, so it becomes easier. In fact, you can actually look at all the carbon materials. Today, what you find, nanotube, nanowire, you have charcoal, you have graphene, graphite, everything. One of the best ways to identify is Raman. Each of them have a different spectra and different ways, and immediately, without even looking at it, you can tell that this is wire, this is just pure porous carbon, this is actually graphene, this is graphite. Any of those things can be done today. And that's how Raman spectroscopy has become a big thing in nanotechnology itself. So in fact, we can make Raman spectrometers, and this is for a person who actually believed in me, and I actually built this Raman spectrometer right here in RGCV, and you can see the demonstration of this by my student. Sorry, I will have to click it. So her voice is not heard, but actually she is explaining that we have a microscope here, and this is the laser is behind it, and she has kept actually just a paracetamol right here, and you are having the laser on. Now you see the red light is coming, and you are collecting back the laser and through the fibers and connecting it to a spectrograph, and she is going to actually record it, and you can get the paracetamol spectra right there. Right? Simple. Right? So this is how it is. It is not that simple. Tomorrow you make it, you will realize there are certain things you may have to ask me how you do it. There are some optics issues here, and that is why many people don't make it. But I have, throughout my life, made my own spectrometers, and I have actually done all my experiments on my spectrometers. So that's why I'm so confident. And actually, this is for diagnostic purposes that in biology, which I'm actually trying to do. This was for Alzheimer's, which I was actually looking at, to be having a portable system which can go around. And this is what it is. So in fact, today, Raman spectrometers can be as simple as this. There is a laser, and this is a mobile type thing. You can actually just you are talking about organic fruits, right? What is, you are believing and paying money, right? Do you really know that there is no pesticide on it? So you can actually find out the pesticide by just incidenting a laser on that and seeing what is the type of pesticides used in your locality and find out whether it is really organic or not. So this is something which is a big thing. By the way, this is more important if I am actually making an Ayurvedic drug. Ayurvedic drug I'm making, if my actual plants have been sprayed with pesticides, your pesticide will be there in your Ayurvedic preparation. Serious matter. And that's what we are trying to actually solve now to do that. Fruits are okay, you have a lot of money, so you can pay. But Ayurveda is going to actually kill you if you are actually having pesticides on the plants, which are actually the source for all of these things. So you realize what is the importance of it. Now I will actually show you, for the interest of physicists and biologists, and I will actually make it simple, how I use a tool like, I was talking about vibrations of molecules. But what I'm going to say is, I'm using the same Raman to prove electronic transitions. So electronic transitions and vibrations are quite different. So how do I actually use it? So this is a technique very rarely used many times by the electronics people. But I am showing that we were the first to actually do these kinds of experiments. So it's for the motivating the students that when you think about a problem, can I actually use my tool in a totally different way from what others use it? And this is one of the things where we are talking about topological transitions. Topological transitions are there in high energy physics. There are in many other places topological transitions are there. It is actually coined from there, and it has come to condensed matter actually. So what I am actually doing is I am actually trying to perturb the machine. So I always say this, that if I want to know about you, if I want to know your potential, How do I actually know your potential for a particular job? The way is to put stress on you. If you break down, you are useless. If you don't break down, you're okay. That means you should not have any change when you are stressed. So I actually use to study materials by actually applying two parameters. One is temperature, another one is pressure. And pressure is a very, very important parameter because it's a clean perturbant. Pressure only changes the volume. And when you change the volume, you are actually squishing things. And when you are squishing things, a lot of things happen to the material. So what is pressure? Force per unit area. And you can see your center of Earth is about 360 gigapascals. To tell you in atmospheres, it's 3.6 million atmospheres. So that is the pressure in which the center of Earth is there. Okay, and this pressure is where you have iron. Iron is actually present. You know that iron is the reason why we have magnetic field, and it is actually in a molten condition. So people have been trying to simulate this in lab. Can we actually simulate such conditions? Yes. You can use diamond anvil cells. So you have two diamonds, whichever diamond you wear, that exactly the diamonds I use. And I have flattened one of the tips of the diamond to a small size. And I put a metal gasket inside and put a sample plus your liquid hydrostaticity. I actually put it, and then I pressurize it. How do I generate such a pressure? If I take 5 elephants, each of them are 5 tons each, and I actually put them onto a surface which tapers down to 1 square millimeter. If I bring down to 1 square millimeter, that means 5 is 5.3 tons, 5.3 elephants together. If I put it, it's equal to 3.6 million atmospheres. And if I put the iron underneath that, I can actually get the situation exactly. So this is a simulation, but actually I have reached 3.6 million atmospheres with hydrogen. And that was because of the interest in universe itself, where maximum hydrogen is present in which planet? In Jupiter. And Jupiter's hydrogen content is very, very interesting to study. People are talking about superconducting hydrogen and other things there. And so that was when I reached 3.6 million atmospheres on this particular material. So I actually use very simple things. It's just, you can hold it in this and I can actually produce that kind of a pressure. Because the diamonds are transparent to light, you can actually pass light through it and you can see the light passes through it and you can do Raman on it. Now, what is this topological transition? Or there is one interesting concept called topological insulators. So topology means the shape, size on top of it. Now you can see that a mug which has a hole here, that is the invariance part of it. I can take the mug and convert it into a donut without breaking the surface. Without breaking the surface, I can do. You see the animation here? I've gone from a cup, which is a cup, and you can see inside layer comes out and it actually forms without breaking the complete topology. So this is, and the whole is the topological invariance, which is there. So this is a mathematical concept. And in material science, it is a very interesting concept when you have a topological insulator, because you know insulator is band gap is there, right? There is a conduction band and valence band, there is a gap. Now when you start bringing the gap together, usually it will become semi-metal and then it will become a metal in normal conditions. That is what happens. That's what normally happens. But if suppose that doesn't happen, if you actually suddenly bring it down such that some part of the valence band characteristics goes into the conduction band and conduction band goes into the valence band, then suddenly there is a difference. It was a band insulator. Now the surface actually becomes conducting. So the surface is conducting, but the bulk is actually insulating. So these are the topological insulators, and they are very, very important because this doesn't happen in all types of material. As I said, when you bring the band gap closer, most of the material will go to a semiconductor and then it will go into a metal. But these are materials because they have a very strong spin orbit coupling. And because of this, that this becomes a very interesting material. Why are they important? Because if these surface states have Majorana fermions, then it can actually be leading to a computation, quantum computing material. And similarly, if you actually have some locked properties, spin momentum locking, then it becomes faster electronics. That means you can have race memory or various other kinds of things, same material. And now, if they are actually having slightly different properties, they can become thermoelectrics, waste to energy conversion. All of these things are possible. So these are very interesting materials, but they are actually nothing but electronic materials. And that's what we are looking at. So you can take this and you can drive this transition happening. But one of the things to understand whether a material would transform to a particular state, that can be simulated, because usually chemists would do, they will add an atom. Because when you add an atom where it should not go, that's called doping. When you dope it or alloy it, then you are creating some sort of a stress. So this can be simulated in a pressure experiment beforehand. So I can apply pressure, and from pressure, I can actually transform these things. Now, that is what is the interesting aspect. So why is this very interesting is because till now we thought of conduction as conduction because of electrons. We never thought about electrons have spin. Now in topological insulators, because their time reversal symmetry is there, that means this cannot reverse itself, the spin cannot reverse itself. The spin will always go in this direction and the other spin will go in that direction. So these two currents will be flowing opposite to each other. And if I populate more of this, then only current will flow this way, and it will be very fast currents. Because unlike the electrons, these spin electrons actually travel very fast. And that means the speed of conductivity goes up. And that's why we can have two-dimensional topological insulators, three-dimensional topological, because the conduction is all on the surface, not inside the bulk. And that's what makes it. So basically, the idea is that if you have this spin, it can never go back. They are all conducting in the opposite directions. Now, one more concept I wanted to tell you is the topology comes from the fact that there is something called the Fermi surface. So this is how the atoms are arranged in a lattice. And you can calculate the energy diagram, energy versus momentum, that is nothing but momentum is here. And so this gives you whether this is a band structure of the electrons. And if I actually go to the three-dimensional part of it, so then I start getting a surface. And this is called the Fermi surface. Now, this Fermi surface defines whether it is a metal, semiconductor, insulator, and all of those things. Now, very interestingly, if I can perturb this surface by actually bringing them closer, and if suppose this closer thing ends up in producing a neck at the surface, and or it makes it a void, then suddenly the topology actually changes. And this topological transition is called electronic topological transition or Lifshitz transitions. And there are many materials which are known to be having this electronic topological transition. These are very interesting materials. Again, they have a lot of electronic properties changing. They can actually produce electronic materials for future use. Now, one of the ways to find out whether that kind of effect is happening is by doing something called angle resolved photo emission spectroscopy. That means you are sending in a photon, knocking off the electron and finding out the energy of the electron. If you find the electron where it is coming from, you can actually make the full the band structure. And that is the method which is used for determining the band structure. So you can see this is the conduction band of a particular nested system where you can see that the band is actually formed. Exactly what you have calculated. So you can visualize it. But only problem is for ARPAS, you need the surface to be very, very clean. It should be not perturbed. It should be freshly cleaved. Now I am pressurizing something inside a liquid. There is no way I can have a clean surface. So ARPAS is impossible. So you cannot get the band structure of the system with ARPAS. And this is where the problem starts. And that is where I brought in a went off. Yeah. So what I have actually done is I cannot use ARPUS in the high pressure conditions. So what I have actually come out with is, can I actually use Raman and prove whether this is a topological transition or not? And that's what I'm actually going to do. So basically, this material BITE is the material which I am looking at, and you can see that it is made up of two materials, BITE3, Bi2Te3, and there is a Bi2Te3 layer, and in between sandwiched is bismuth layer. So the bismuth layer is sandwiched in between. Now if you look at this, it becomes BITE. Now we know that Bi2Te3 is a topological insulator, 3D topological insulator, and this we have actually already proved that it's a weak topological insulator and it is having multiple phase transitions under pressure. Now what we wanted to understand, and it is a very good thermoelectric material, it has been already shown in this particular system. Now what we wanted to know is, when I sandwich a bismuth layer in between, does it have an interesting transition or does it retain its property of topological transition? And that is what we wanted to look at it. I will actually go forward. So one of the ways to say it is a topological transition is to first prove there is no structural transition. When I actually squeeze the material, I should not have a structure change. If I have structural change, that means the band structure changes. So I should first prove that it doesn't have a structural change. So when I squeeze it, I do X-ray crystallography, and I see that up to 4 gigapascals, you can see that there is no transition. But as soon as I reach 4 gigapascals, I start seeing appearance of a new peak. And this, after 6 gigapascal, completely transforms into a new phase. And that is what it is there. So the structural transition is not there below 4 GPa. So this is something I have actually seen. Now, I do Raman, and I said Raman is actually vibrations. So now you can realize that vibrations are actually calculatable. So you can put it in a computer and find out what are the different vibrations which are present in this. Now what I do is, I actually do a pressure dependent study. And as I saw in the case of a X-ray crystallography, you can see at around 5.6, my complete Raman structure is changing, and it is actually changing into a new phase itself. And so it is exactly mimicking what is happening. But what I wanted to see is whether any transformation happens below 4 GPa, because most of the topological transition happens around 1 to 2 GPa, and that's what we are interested. So what we always do in Raman is plot the frequency versus pressure or a temperature. So if it is not having any transition, this will be a monotonically increasing function or a decreasing function. Now you can see that at different points, actually there are some fluctuations happening in the system, and this is where the phase transition happens, and that phase transition completely, it is transformed. So that is a different structure. Now I wanted to look at FWHM, the width of the peak. If the width of the peak is actually related to two things, one is order, second is electronic connection between the vibration. That means electron phonon coupling. So if the width is changing, that means if there is no order change, that means the structural order is not changing, it has to be electronic in nature. So when I do that, you can see at 1 gigapascal, you have a very strong change in the electron photon coupling. And this is basically where we started looking at it. Now that means it's an electronic transition. And now I want to see if this electronic transition can be calculated using your MD simulation, or you do a dynamic DFT calculation. So when you do a DFT calculation, you can see band structure, and you can see that when you look at the Brillouin zone, and you can see that there is a change in the nesting. That means there is a void which is being created. So which means it's an electronic topological transition happening in this phase. So this is one of the ways to understand what is happening. Now, the importance of this is, now if I actually dope or alloy change it, I can immediately see that I can have a room temperature material which can have this property. And that's what leads to it. So basically, there is a transition which happens. And here, as seen in our calculations, you can see that it is becoming a semi-metal, and there is a metal insulator transition which is happening in the system. So both, all of these things are happening. Now, I'll go to another clinical problem, and I will actually stop with that in a short time. Now, when I am actually looking at proteins, it is a very complicated system. It's not easy to actually simulate everything, because in a protein, you have lakhs of molecules, lakhs of atoms. And to simulate that becomes a very, very difficult thing. But in Raman, it is very, very interesting that if I actually look at this is the absorption of light with the protein. And this is a very important protein in your body, which is called the myoglobin. It is having heme. Heme is the one which carries the oxygen, right? So this is a myoglobin which is present in your body, and this has this kind of a structure. Now you can see that if I am using different wavelengths of light, I actually get different Raman, because you see pi star, sigma star, and n sigma star and pi star transitions are actually electronic transitions which are coupled with the vibrations. Now, if I use 206 as my wavelength of light, I am not getting anything other than the secondary structure, that is alpha helix peaks, which is what is seen here, because this is actually because of hydrogen bonding. You know that most of your proteins are made up of amino acids, and amino acids link up together by a peptide bond, C double bond O NH. C double bond O stretching frequency and the bending frequency of NH is exactly same, and because of which there is a coupling happens, and that means this vibrations actually are coupled vibrations of the peptide. And because this is where the hydrogen bonding happens, the hydrogen bonding actually is the reason whether something is alpha helical, something is beta sheets, something is anti-parallel beta sheets, or random coils. All of these things actually come up because of that. So this is very, very important, and this frequency directly tells me what is the characteristics of this folding, and that tells me about the structure. Now, if I change the frequency to 229, immediately I see that, immediately I see there are another moiety amino acid which is called tryptophan, and there are multiple tryptophans, and these tryptophans get activated, and my spectra doesn't show this, but it only shows the tryptophan. And if I actually go to the 415, that is the absorption of the heme, and at that point I only get the heme spectra. So you can see Raman I had told is wavelength independent, but actually not. It is resonant Raman also is there. So you can actually precisely send in wavelength of light to pick up a particular molecule inside that. So this becomes very, very useful in actually understanding biological systems very much. Why is it so important? Because today we have something called, you have blocks. You have blocks in your arteries. Now, blocks in your artery happens because there is a plaque formation. This plaque is nothing but lipid forms, and then there is a calcification. This block is very, very important to know whether a stent will work or not. The stent will work. It is a fluid dynamics problem because your blood is flowing, and if suppose the plaque gets dislodged, if it's a soft plaque, it gets dislodged. If I put a stent, that plaque will come inside the stent and actually form a block again. Stent has blocks. Many people have had this problem that the stent has been put, again they are having a heart attack, and the same place, because there is a deposition in it. Because if it is a soft plaque, you should not put a stent. If it is a hard plaque, that means calcification, you put a stent, this will remain there and you will have no problem. So that's why many people actually have this problem. They put the stent, again they had a heart attack on the same place, exactly. Okay, so this is something which is very important. Now you can realize Raman, because you can actually have a Raman fiber go inside through the catheter. You can actually do this in situ, but this is an ex vivo. So you can see a normal arteries Raman, and this is the lipid rich plaque, which means it's soft plaque, and you can see a totally different spectra, and you can see a calcified plaque, which is basically because of hydroxyperite, calcium hydroxyperite, you have a strong signature. So if I can actually, before putting this stent, if I can actually find out which type of plaque is there, the doctor can actually decide whether to put a stent or not to put a stent. Because if it is a soft plaque, leave it. You should not do anything. He will be all right, because after some time the plaque will go away. So this is some things which the decisions can be done. Similarly, one of the biggest problem is breast cancer, and this is a very rampant thing today in our female population. Most of the times the breast cancer has to be detected by mammogram, which is what you do. But you can realize if the breast tissues are actually fatty or dense. If it is dense, it's very difficult to find out a lesion. Whereas in a fatty breast, you can actually find the lesion. So there is always a confusion whether you can actually find out whether this lesion is there, and this lesion needs to be actually looked at very carefully. Now, if I do this is a live surgery happening, and this data is collected on a live patient while the fibroid is being removed, and it is a cancerous fibroid. You can realize that the tissues are normal, and you can see the red line is actually a statistic of many spectra, and you can see in 1 second I can actually get the full spectrum. Now, if it is cancerous, you can see it's totally different spectrum. And now you can see it's like light and day. I can exactly tell the doctor how much of tissues have to be removed, because today in cancer, the most important thing is the margin. You should not leave any cancerous tissues back. You should remove off all the cancerous tissues, because the relapse is a very, very important problem. So you can see the importance of using this kind of a thing. So in histopathology also, it is a very, very important thing. You can take tissue sections and you can actually see this is a pathologist who has actually done it by staining, and this is what a Raman spectra of the system is. And you can see at the exact point the brown tissues here are the ones which are matching. But it is also very careful. So this is a complete tissue which is completely cancerous. You can see that it is completely cancerous in this system. But what you have to realize is that there are some false negatives also. There is no, this is a very clean tissue, but you do see some appearance. So there is a second need to be looked at very carefully, whether there are some cells already present in that which are actually cancerous. So this is becoming more and more used now clinically, and we can actually look at it. Now, I am going to stop with this one example. So this is an example which I have actually worked with a clinician. Basically, this is in Trivandrum Chaitanya Hospital, which is there. You would have seen that hospital. This doctor is there, Minumathan. You can actually get cataract operation done. He is a very good cataract surgeon. So he came to me with a question. The question was, he was actually doing one of the major issues in India is, or anywhere, until you stop seeing anything, you don't go to the cataract surgery. That means it's a matured cataract. So matured cataract, what happens is that you have to actually do the surgery, you have to use a dye. So basically what happens is that how do you do the cataract surgery? So you can actually, if you are not using the laser, if you are actually using just so you put in a typane blue, which is a staining dye. For epithelial tissues, it can stain. And if you stain it, you get a bluish color to the epithelial cell. So you are actually making a tear. So they take it like this and make a circular tear. That's called capsulorhexis. Once you do it, you can see as if the the tissue is getting torn, you get more and more blue color. So that tells them that you are not actually, you have made the complete tear. If you don't make a complete tear, you cannot put the artificial lens inside. So this is why they put the type in blue. Now, after this, they will use a thing to coagulate all of this, and suction they'll do, and they'll put the artificial lens. Now, the problem was, in some cases, the vision doesn't come back. The question was, is there a problem? What is happening in this case? In something like 5 to 6% of the cases, you are not getting back the vision. So after a cataract surgeon, surgery, you put in the lens, you should get perfect vision. There is no need of actually loss of vision, because the lens goes and sits back, because you have already calculated what your lens requirements are. This was the question. What is happening to the, because it's a capsule. The capsule is actually put in. Now, there are only two reasons why this can happen. One is the lens capsule becomes very rigid, or lens capsule is actually becoming, elasticity is lost. So if elasticity is lost, it will hold the lens in different angles, and that's where you lose the vision. So the question was, what is happening to the lens capsule? And there is no technique in the world to actually answer this question. This question was what was puzzling the whole of cataract community, and there are multiple papers they have tried to do it, and they couldn't get the solution. So he came. So what I looked at is, what is the lens capsule material? The lens capsule material is nothing but collagen, and collagen is actually a triple helical system. So it is just a triple helical system which actually makes a network, and then you have sulfur-sulfur bond, which is called the 7s domain, and it actually gets connected to each other. So it is like a network of this thing. It is actually there, because most of it is porous, you can see through it. Nothing, vision is not blocked, but most of it is actually fiber. And if you look at it, you can realize some more proteins are there below that, but this is not major. This is the collagen, which is collagen 4, which is the major thing. So as soon as I looked at it, I actually thought like a normal human being who is not working in biology. I said, it looks like my fishing net. So if it is a fishing net, very beautiful, it has elasticity and it is strong, right? The moment it actually starts, you use it, you start making networking here and there. So cross linkages, if it happens, you will realize the elasticity is already gone. Now, the question was, can I actually detect? Another thing is, you can see that the braids open up, again the elasticity is gone. So can I actually detect so this is a triple helix. Can I actually see whether there is a structural change happening in the system? And I told you, the secondary structure, that is alpha helix, beta sheets, and random coils is through that amide 1 vibrations. So if I can look at that amide 1 vibrations, can I actually predict whether there is a change in the helical structure? So that was the question. And indeed, what I realized is, when I use different dilutions of trypan blue, you can see this is as concentrated as in the bottle, and this is 5 times dilution, this is 10 times dilution, this is 50 times dilution, and this is 100 times dilution. I do it. This is the percentage of alpha helical content. So you can see the concentrated trypan blue is actually changing the alpha helical content. That means alpha helix is becoming opening up. And from the Raman, I'm cutting short this thing. In Raman, I can actually see the presence of a loose thing which is happening. Now, what I also realized is that it is not the trypan blue alone. You need the light. If I don't put the light, it doesn't actually cause. Because when I'm using a microscope to see this, or Raman scope, I have to put white light. The moment I put the white light is the effect. You can realize that if these are two concentrations, this is as concentrated as it is in the bottle, and this is the concentration with 5 times dilution. And you can realize that as soon as you start the experiment, within 10 seconds, as concentrated goes more than 60% loss of alpha helical content. That means the light and the type N blue is the problem. Now you can realize it's a photochemical reaction. Type N blue in presence of light is actually giving reactive oxygen species. And any reactive oxygen species will change the protein structure. This is a well-known thing. So that is what is happening. Now, what is the interesting aspect is, in the 5 times dilution which the doctor uses, up to 10 seconds, there is absolutely no change. It's only after the 10 seconds this effect is coming, 30 seconds. You see the alpha helical contents changing. So this is a very important learning, one. Second thing is cross linkages I wanted to see. Now cross linkages also I can test by doing a simple physics experiment. Take the lens capsule material, stress by strain. Okay, you do a stress by strain. This is done on a goat's eye, not by me. Another group had done. They took the lens material, applied stress, and measured the strain of that. How much did it actually change? So if this is shallower, that means it is elastic. When it is actually when it is actually proper elastic, it will have a very smooth curve developing, and as soon as it gets cross-linked higher, it actually gets stiffer. So the stiffness actually increases. Now, why does it happen? If I put light, nothing happens. If I put type N blue alone, nothing happens. If I put type N blue and light at different light intensities, it happens. Now, there is a material which is there, chemical, which is called glutaraldehyde. And if I put glutaraldehyde, because it's an oxidizing agent, sulfur actually gets oxidized and it forms sulfur-sulfur bonds. And this sulfur-sulfur bond actually causes cross linkages. And that's why this is happening. Now, I wanted to see where if I don't use, if I put the light and the type N blue, does it actually cause? So I did the Raman. You can realize this is the sulfur-sulfur bond peak, and this appears in glutaraldehyde, and exactly at the same point, it actually has the same thing. So basically, two things are happening. If you expose if you put in your type N blue and put a light for a longer time, then you are actually causing two damages. One is the braids are opening up. That means it is becoming unstructured. Second is it is getting interconnected. So that means it is becoming stiffer. So naturally, that is the reason why it is happening. Now the question was, how long can they do the surgery? So the question is, in 5 times dilution, you can only have this surgery done 10 seconds. Now, is this a feasible thing? And surprisingly, yes. The thing is that just after the capsular access, they actually put a lot of water. So it is diluted. Right? So only till the capsular access, they actually have a concentrated system. After that, it is actually 100% diluted because a lot of water is used to, and that completely gets it. Now, I asked him, how much time does it take for you to do the capsular access? 6 seconds. 5 to 6 seconds. And that is why 95% of time they are, the day they actually take a little longer, it's a failure. And they agreed. And now this is actually appreciated by the American Cataract Society, European Cataract Society, as well as by Indian Cataract Society. So they know now that it is because of this reason. So if by chance they actually have a little delay in this capsular access because of something else happened, their lens will not sit back again correctly. This is one very interesting aspect. So in fact, there are a lot of challenges in this particular type of experiments because this is where AI has to come in. So all this spectra, if you want common man to use it or normal people to use it, you need to bring in AI into this whole phenomena. So AI with the Raman will be a very, very potential tool for future of how all material science, physics, chemistry, or even if you are looking at extraterrestrial eyes or any of those things, you will actually require this aspect. With that, I'll thank all my students, both in RGCB as well as in JNCSR, for being the people. I always say, if I don't have good students, I cannot actually do anything here. So all of these guys are great, and that is why I'm able to stand in front of you and tell you, thank you very much.
Thank you, Professor Narayana, for passionately explaining the basics of Raman spectroscopy and explaining to us in a very simple way the applications, the tremendous applications in various fields, including material science, biology, and healthcare. Thank you very much, sir.
About the swimming pool, right?
Yes, yes.
Where the shallow part of the swimming pool is blue and the
Green.
shallow is green and the deep one is blue.
Yes.
But in the ocean, you said it is the fact that you are having salty water in the top and clearer water in the bottom. That change in the refractive index along with the total internal reflection is what is giving rise to the different colors. In a swimming pool, you expect to be uniform composition, right?
Correct.
So why is it that
you have tiles, no? White tiles.
so that is the reflection from the
So
tiles?
up to about even half a kilometer, the light will go through. You can actually get light. You can see through up to about maybe about 500 meters or something like that. You can actually see light coming in any water. So this is the white tiles which is actually reflecting back. And that's why I said you should not have blue tiles, you should have white tiles, because it reflects all light. It doesn't specifically reflect a particular light, right? So all the clean swimming pool or the Olympic standard swimming pool will not have anything other than white light. And Olympic standard pools, you will see a lot of videos and everything, it's all blue in color, because the depth is actually more than 6 to 8 meters. Okay. 6 to 8 feet. It's more than 6 to 8 feet. So that's why it's the after about a meter and above is when the coloration starts. So it's that is where the color comes. Yeah.
Just I was wondering actually, how about the damage threshold of this biological sample? If you use lasers, so how much typical laser power you can tolerate, and then are you limited by the laser power?
Of course, that is if a simple experiment for laser damage. Before you go, you take the sunlight and use your lens. You will burn your skin, right?
Yeah.
So actually, how much is the wattage of that? You can realize. So its power density is very, very important. So in most of the biological samples, we are using 1 milliwatt laser. We don't use more than 1 milliwatt, or maximum 10 milliwatts. That is the maximum we use. And we first check whether it is burning the sample. One of the ways to know whether it is burning the sample is if you start seeing carbon spectra. The moment your skin or any biological system is organic, so it will produce immediately carbon. So you will get the 1500 peak, 1550 peak, and you will get the 1350 peak. These two peaks will come up if it is carbonized immediately.
Yeah.
So we will actually make sure that the powers which we use is very, very low, and only increase it slightly so that we are not compromising on the burning. So your question is very valid. So you have to start with a very low power.
Yeah, in that, just in continuation of that, because nowadays a lot of research going toward the quantum imaging. So do you think that quantum imaging will help actually because quantum imaging in low light conditions it gives like a better resolution, or your SNR will be better. So anything is explored in this direction?
Not explored, but yes, you can actually use low resolution and you can enhance the signal. So basically, if you look at any of these things, if it is low, then you have to accumulate for a longer time. The intensity is low, then you have to see whether over a period of time. All of these things depend on absorption. If there is no absorption of that particular wavelength of light, then you are safe. You can actually, you may not heat up. It's only because of the absorption that happens. So you can even move the wavelength of light to different wavelengths to test out which wavelength is not actually affecting it.
Sure.
So the experiment on the breast tissue, while it was done, I showed you that it was 100 milliwatts. 100 milliwatts 1 second. So 1 second you are putting 100 milliwatts. It won't burn. Okay. And breast tissues may not actually absorb. It's already not the brown skin. It's actually removed and you are actually accessing directly the fibers there. So they do not absorb in the 785 wavelength which was used. So it doesn't absorb in the IR region. So that is why it was possible to do with 100 milliwatts 1 second. You could actually do those experiments.
Sure. Thank you very much.
So actually Raman is not a quantitative tool in the normal sense because it is a scattering process. So what I want you, all of you to realize is absorption is quantitative. If one photon goes, one photon gets absorbed. But in scattering, it's a chance factor. Thousands of photons go, one may be scattered. And that is why it is never a quantitative tool. Now, to make it a quantitative, you have to have a scale. So normally what people will do is, they will do a different concentration, they will actually plot. If it is in this linear scale, you can use it for quantitative measurements. So that's a relative quantitativeness. So you don't actually do it in exactly. If I say this is there, I should have already calibrated that if it was this concentration, I will get this intensity. So that is how you do it. So it is a relative calibration which you do. So quantitative, Raman, we have to be very careful. Until unless you have a linear relationship, you cannot use it for quantitative measurements. Yeah. BITE3 T.
Yeah. So for that simulation, you used Raman in what way?
So you are asking, I use Raman, I use X-ray, I use DFT calculations.
Yeah.
Yes. Yeah.
And you were trying to bring the band gaps closer and trying to observe what is exactly happening. Like, is it a
topological transition or it is not a topological transition?
Yeah. So can we actually simulate, like, if we can find out the work function change through that simulation?
Simulation, you can actually find out all material properties, complete material properties.
Through that same simulation.
Same simulations, you can actually find out. Because what I am actually doing is, in computer simulation, I am bringing the atoms closer. So the volume I am changing. The moment I change the volume, the atom positions are coming closer. So the distance between the atoms change. So the band structure keeps modulating that. And just like the band structure, all the material properties will change. The elasticity will change. The stress strain relations will change. You can have many other parameters which can be drawn. So DFT can actually calculate all parameters of the material. DFT is a prediction tool. So you can actually predict any of those things.
So this pressure simulation was just to have a physical simulation of
what I was doing the experiment.
DFT. Okay.
So once I have seen that it is an electronic transition, I wanted to confirm what kind of electronic transition it was. So see, I cannot say from Raman whether it is topological transition or it is a simple electronic transition of metal insulator or what it is. I cannot say. So that is where I actually look at what is exactly happening to the band structure. So when I look at the band structure, I see that there are nesting happening. That means in the Brillouin zone, you are having voids and you are actually creating some necks. And this is actually exactly mimicking Lifshitz transition or the topological, electronic topological transition.
So basically, when we dope, we are bringing that together, and
so
we are increasing stress.
now I have found that BI layer. See, when BI layer is not there, it is a topological insulator. When I have a BI layer, I am actually converting the topological insulator to a electronic topological transition. So now I know that if I can fine tune this by actually putting something which can exactly give the same kind of volume change, I can actually immediately get the material at room temperature. What will give me the property what I am getting there. So I know what kind of things I cannot use it. I can even realize that if I actually have something else sandwiching between the two layers, I can. So you do heterostructures, right? You put a BITI and you put another layer of BITI. So you can actually introduce these kinds of stresses. So the property which you wanted would have gone. So I can give that kind of inputs from my research. That's what it is. Do you understand? Yeah. Go ahead. And mic in the distance, good. Yeah, I was able to hear your good evening. Ha, okay, very interesting. So the whole point is that whatever interpretation I was doing is because of my experience, right? But how much can I actually interpret a spectra? The spectra is looking like this. To you, it will look totally different. For me, I can see a small variation in that and say that there is, you may say I'm making a needle, I mean, I'm making a mole out of, what do you call a mountain out of a mole, right? So that is what is the problem, that trust between me and you. Because I am interpreting, because I have a vast experience, I am able to interpret. Same data I would have given you, you would have said nothing is happening in this. Right? So how do I actually break that? If I have a statistics, like I have done this millions of time and produced many different spectra, and my AI program actually looks at it whether any changes are happening, then my AI program will be able to clearly tell me what are the changes which are happening in the system over a period of huge number of data. And this becomes very, very useful, let us say, in a case where I am actually trying to figure out what I saw is that in a very tiny quantity, I saw something. If I have done it over a large system and I know that the spectra will look like this in multiple different variations, I do it there, I can do it. An example for this is if I am actually in the space mission, I put my Raman spectrometer there and I'm actually taking a rover and going around and testing all kinds of things there. Let us say, hypothetical. Then I am actually seeing water, ice, and a particular spectra comes. If my AI has done a huge number of study on various different forms of ice, then I can actually be very sure that I have found ice or not. Right? I'm just giving an example which is more closer to this institute. That's why. Similarly, if I would have given an example for a biology, then I am actually looking at tissues variations, right? If I am taking, say, skin cancer, or I am looking at oral cancer, I'm actually doing a complete scan of it. I want to know whether this particular individual's lesions are actually cancerous. If I have actually done this quite a lot of time, then I know that these signatures actually means that this is cancer. It may not be the real tissue. Right? So that kind of thing. So AI actually helps me in actually making that conclusions error independent, and expert, non-expert can also do it, taking it out of an expert's domain. Did I answer the question? Yeah, thank you. Yeah. Huh?
The Raman spectrum of the apple.
Huh.
It was not a dark condition. So
yeah. So okay, since you have done Raman, you always switch off all the lights and do it. Right. Actually, in principle, if my signature which I am getting is stronger than the background noise, I can actually filter it out. Another way, what I will do is I will take a Raman spectra on a clean say, see what all things come because of this. I'll actually, those things I will actually subtract it out.
Okay.
So I can do it in a bright sunlight. There is no problem. So actually, because we do on experiments where we don't know what I am going to expect.
Okay.
That is why we would not like any other thing to interfere. But when I am actually looking for a pesticide, now how do I know what are the pesticides used in US is different from pesticides used in India. So I know what are the different pesticides which they will use for a particular crop, right? So I will do the Raman of all those pesticides, and I will know the specific signatures of each of these pesticides. And when I am doing it, I am only looking for that pesticide. So if I do a subtraction of all the background, doesn't matter. I'll get that peak, right? Now you understood.
Yes, sir.
So you can do it in daylight.
Yes.
Otherwise, you cannot give it to a farmer, or you cannot give it to an industry.
Exactly.
That's what.
Thank you, sir.
I'm sure that there will be many more questions, but then because of paucity of time, we are forced to close the session. Once again, thank you very much, sir. And as a token of appreciation,
I should jump down.
Words, yeah. Few words before you conclude the session. So it has been a pleasure to have.
Is it on? Yeah. Yeah. To have Chandrabhas. Actually, I saw him after 30 years of our IISc days, and of course we were both very thin. We had almost 5-year overlap at IISc in Bangalore, and I used to only visit Raman building, and you were in the
Raman building.
so we didn't meet that often apart from Gymkhana.
Yes, and football ground.
Yeah. So he's also a student of Professor A.K. Sood, who is the principal scientific advisor, and it's quite amazing. I am getting amazed, he was a physicist. How come he has picked up all these, which I don't understand, but today's your talk, I could make out quite a few things. Thank you very much, for coming over. And I hope our students got this flavor of, how his smartness, being a, pure physicist, experimentalist, and then, just exploring what all places, his technique can be applied. And today, being the director of a biotech institute, I will be daring to get into domain of biology that much. So that shows the sort of openness. So I think for modern day, it is very important for all the students to keep wherever you're, getting your training, that can be applied actually to many, many different fields. So that's thank you very much, Chandrabhas.
Thank you. Thank you.
This rocket will eventually take
will
you
get
to the Mars.
us.
Want your technology.
But it's very difficult to convince the ISRO person.
We'll try together.